Formation and development of binary stars. Binary stars, also known as double stars, are a common type of star system in the universe. They consist of two stars that orbit around a common center of mass, bound together by the force of gravity. In this article, we will explore the formation and development of binary stars. Binary stars are thought to form in much the same way as single stars, through the gravitational collapse of a cloud of gas and dust. As the cloud collapses, it begins to spin, forming a flattened disk of material around a central protostar. Over time, the protostar becomes more massive and begins to heat up, eventually igniting nuclear fusion in its core and becoming a fully fledged star. In some cases, however, the cloud may not collapse into a single protostar, but instead may fragment into two or more separate clumps of gas and dust. If these clumps are massive enough and close enough together, they may begin to orbit each other and form a binary star system. The exact conditions that lead to the formation of binary stars are not fully understood, but it is thought that they may be influenced by a number of factors, including the initial mass and rotation of the cloud, the presence of magnetic fields, and the effects of nearby stars or galaxies. Once formed, binary star systems can undergo a complex and dynamic evolution, shaped by a number of factors, including the mass and distance of the stars, their orbital eccentricity, and their age. One important factor that influences the evolution of binary stars is their mass ratio, or the ratio of the masses of the two stars. In general, binary stars with similar masses tend to evolve more slowly and have longer lifetimes than those with a large mass ratio, where one star is much more massive than the other. In these cases, the more massive star may undergo rapid evolution and eventually become a supernova, while the less massive star may be ejected from the system or become a white dwarf. Another important factor that influences the evolution of binary stars is their orbital eccentricity, or the degree to which their orbit deviates from a perfect circle. Binary stars with highly eccentric orbits may undergo tidal interactions that can cause them to exchange mass or even merge together, while those with more circular orbits may remain stable over long periods of time. In recent years, advances in observational techniques and computer modeling have led to many exciting discoveries and breakthroughs in the study of binary stars. For example, the discovery of binary black holes and binary neutron stars has provided important insights into the physics of extreme gravitational phenomena, while the study of eclipsing binary stars has provided valuable information about the properties and behavior of these systems. Moreover, the study of binary stars also has important practical applications for astronomy and space exploration. For example, binary stars can be used as a tool for measuring distances to other galaxies, through a technique known as the standard candle method. This involves using the known properties of certain types of binary stars, such as the period of their orbits and the luminosity of their stars, to calculate their distance from Earth. In addition, binary stars can also be used to study the properties of exoplanets, or planets that orbit stars other than the Sun. By measuring the gravitational influence of a planet on its host star, scientists can determine the planet's mass and orbit, as well as its potential habitability. Overall, the study of binary stars is a fascinating and important area of research that has broad implications for our understanding of the universe and our place in it. With ongoing advances in observational techniques and computer modeling, we can look forward to many more exciting discoveries and breakthroughs in this field in the years to come. Another interesting aspect of binary stars is their variability. Many binary stars exhibit variations in their brightness or spectral properties over time, as a result of their orbital motion or other physical processes. One type of binary star that exhibits variability is the eclipsing binary. These are binary systems where one star passes in front of the other from our line of sight, causing the total brightness of the system to periodically decrease. By measuring the depth and duration of the eclipses, astronomers can determine the size, shape, and orientation of the stars, as well as their mass and density. Another type of variable binary star is the spectroscopic binary. In these systems, the stars are too close together to be resolved as separate objects, but their spectral lines exhibit periodic shifts due to their orbital motion. By analyzing these shifts, astronomers can determine the masses, orbits, and other properties of the stars. Binary stars can also exhibit other types of variability, such as pulsations, flares, and eruptions. These phenomena can provide important insights into the internal structure and dynamics of the stars, as well as into the physical processes that govern their behavior. Binary stars are thought to form through the same process as single stars, which is the gravitational collapse of a cloud of gas and dust. This process is initiated by a disturbance, such as a shock wave from a nearby supernova, a collision between two clouds, or a gravitational interaction with another star or galaxy. As the cloud of gas and dust collapses, it begins to spin faster and faster, due to the conservation of angular momentum. This spinning causes the cloud to flatten into a disk shape, with the protostar forming at the center of the disk. Over time, the protostar becomes more massive, as it accretes more and more material from the disk, and it begins to heat up, eventually reaching temperatures and pressures high enough to ignite nuclear fusion in its core. At this point, the protostar becomes a fully fledged star. In some cases, the protostar may not be alone in the disk. If the cloud of gas and dust is sufficiently large and dense, it may fragment into two or more separate clumps, each of which can form a protostar. If these clumps are close enough together, they may begin to orbit around each other and form a binary star system. The exact conditions that lead to the formation of binary stars are not fully understood, but it is thought that they may be influenced by a number of factors, including the initial mass and rotation of the cloud, the presence of magnetic fields, and the effects of nearby stars or galaxies. Binary stars can have a wide range of properties, depending on the masses, separation distances, and orbital eccentricities of the stars. Some binary systems have stars that are similar in mass and are close together, while others have stars that are vastly different in mass and separated by thousands of astronomical units. In some cases, the cloud of gas and dust may not collapse into a single protostar, but instead may fragment into multiple clumps that form several protostars. If these clumps are massive enough and close enough together, they may begin to orbit each other and form a binary star system. The fragmentation process is influenced by a number of factors, including the initial conditions of the cloud, such as its temperature, density, and angular momentum. For example, a cloud with a higher angular momentum is more likely to fragment into multiple clumps than a cloud with lower angular momentum. Once the protostars are formed, Their mutual gravitational attraction causes them to orbit around their common center of mass. The orbital properties of binary stars depend on the masses and separation distances of the stars, as well as the initial conditions of the cloud. For example, protostars that form close together in the cloud may have tighter and more circular orbits than those that form farther apart. The formation of binary stars is still not fully understood, and it is an active area of research in astrophysics.
Classification of different types of galaxies. Galaxies are immense collections of stars, gas, dust, and dark matter that are held together by gravity. There are several types of galaxies, and scientists have classified them based on their morphology or shape. Here is an overview of the different types of galaxies. Spiral galaxies. Spiral galaxies are one of the most common types of galaxies, and they have a flat disc-like structure with a central bulge and spiral arms that extend outwards. They are further classified into two subtypes, normal spirals and barred spirals. Normal spirals have a smooth disc with a central bulge, while barred spirals have a bar-like structure in the center with spiral arms emanating from the ends of the bar. Elliptical galaxies. Elliptical galaxies are oval or spherical in shape and have no spiral arms. They are classified based on their degree of flattening, ranging from E0, spherical, to E7, highly elongated. Elliptical galaxies are the most common type of galaxy found in galaxy clusters. Lenticular galaxies. Lenticular galaxies, also known as S0 galaxies, have a central bulge like elliptical galaxies, but they also have a disc-like structure similar to spiral galaxies. However, they lack spiral arms, and their disks are much flatter than those of spiral galaxies. Irregular galaxies. Irregular galaxies have no distinct shape or structure and are often chaotic and asymmetrical. They are further classified into two types, Ir-I and Ir-II. Ir-I galaxies have some structure and show evidence of recent star formation, while Ir-II galaxies are more chaotic and lack structure. Dwarf galaxies. Dwarf galaxies are smaller than other types of galaxies and often have irregular shapes. They are classified based on their morphology, such as dwarf elliptical, dwarf irregular, and dwarf spheroidal galaxies. Moreover, studying the different types of galaxies also helps us to understand the distribution and behavior of dark matter in the universe. Dark matter is a mysterious substance that does not interact with light, and its existence can only be inferred by its gravitational effects on visible matter. Scientists believe that the distribution of dark matter plays a crucial role in the formation and evolution of galaxies. The study of galaxies also helps us to understand the history of the universe. Galaxies are thought to have formed a few 100 million years after the Big Bang, and their evolution over billions of years is closely tied to the expansion and evolution of the universe itself. By studying the different types of galaxies at different distances and ages, scientists can reconstruct the history of the universe and gain insights into the processes that shaped it. In recent years, advances in technology and observational techniques have led to many exciting discoveries in the field of galactic astronomy. For example, the discovery of supermassive black holes at the centers of galaxies has revolutionized our understanding of how galaxies form and evolve. Moreover, the discovery of exoplanets around other stars has opened up new avenues of research into the search for life beyond Earth. The classification of different types of galaxies is an essential tool in the study of galactic astronomy. It helps us to understand the formation and evolution of galaxies, the distribution of dark matter, and the history of the universe itself. With ongoing advances in technology and observational techniques, we can look forward to many more exciting discoveries in the field of galactic astronomy in the years to come. In addition, the classification of galaxies also provides valuable insights into the physical processes that govern the formation and evolution of galaxies. For example, the spiral arms in spiral galaxies are thought to be caused by density waves that compress gas and trigger the formation of new stars. Elliptical galaxies, on the other hand, are thought to form through a process of mergers and interactions between smaller galaxies. The study of galaxies also helps us to understand the nature of dark energy, a mysterious force that is thought to be driving the accelerated expansion of the universe. By studying the distribution and motion of galaxies at different distances and ages, scientists can infer the properties of dark energy and test various theories about its nature. Moreover, the study of galaxies has practical applications in the field of astrophysics and cosmology. For example, astronomers use galaxies as standard candles to measure distances to faraway objects and map the large-scale structure of the universe. This information can be used to test models of the universe and constrain the values of cosmological parameters such as the Hubble constant and the dark matter density. Spiral galaxies are one of the most visually striking types of galaxies, with their flat disk-like structure and spiral arms. They are believed to be formed from a combination of accretion and gravitational collapse of gas and dust in the early universe. The morphology of spiral galaxies is characterized by a central bulge, which contains old stars, and spiral arms that extend outwards from the bulge, which contain young stars, gas, and dust. The spiral arms in spiral galaxies are thought to be caused by density waves that move through the disk and compress the gas and dust. As the gas and dust become denser, they trigger the formation of new stars, which are often blue and hot. This process is known as star formation, and it is one of the most important processes in the evolution of galaxies. Spiral galaxies are further classified into two subtypes, normal spirals and barred spirals. Normal spirals have a smooth disk with a central bulge and spiral arms that emanate directly from the bulge. Barred spirals, on the other hand, have a bar-like structure in the center of the galaxy, which is believed to be caused by the gravitational influence of a central massive black hole. The spiral arms in barred spirals emanate from the ends of the bar, creating a distinctive spoked wheel pattern. The size and shape of spiral galaxies can vary widely, with some spiral galaxies being as small as a few hundred light-years across, while others can be as large as hundreds of thousands of light-years across. The Milky Way, the galaxy that our solar system is a part of, is a barred spiral galaxy with a diameter of around 100,000 light-years. Elliptical galaxies are another common type of galaxy that are distinct from spiral galaxies in terms of their shape and structure. Unlike spiral galaxies, which have a flat disk-like structure with spiral arms, elliptical galaxies are spherical or oval-shaped and have no spiral arms. They are typically composed of old stars, with little or no ongoing star formation, and contain little or no gas or dust. Elliptical galaxies are classified based on their degree of flattening, with the most spherical galaxies being classified as E0, and the most elongated galaxies being classified as E7. This classification system is based on the apparent ellipticity of the galaxy's shape when viewed from Earth. The structure of elliptical galaxies is dominated by a central region known as the bulge, which contains most of the galaxy's stars. The stars in the bulge are typically old, with low metallicities, and are believed to have formed early in the history of the universe. The outer regions of elliptical galaxies contain fewer stars and are more diffuse. Elliptical galaxies are thought to form through a process of mergers and interactions between smaller galaxies. When two or more galaxies collide, their stars and gas clouds are disrupted and can be flung outwards to form an elliptical galaxy.
Astronomical phenomena on planets and moons in the Solar System. The Solar System is home to a diverse range of planets and moons, each with its own unique set of astronomical phenomena. From the towering volcanoes on Io, one of Jupiter's moons, to the breathtaking auroras on Earth, there is no shortage of celestial wonders to explore. In this article, we will take a closer look at some of the most fascinating astronomical phenomena on planets and moons in the Solar System. Volcanism. Volcanism is a common phenomenon on many planets and moons in the Solar System, including Earth, Venus, Mars, and several of Jupiter's moons, such as Io and Europa. Volcanoes on other planets can be much larger and more active than those on Earth, due to the different geological and atmospheric conditions. For example, Olympus Mons on Mars is the largest volcano in the Solar System, with a height of over 22 kilometers. Auroras. Auroras, also known as the Northern and Southern Lights, are a spectacular natural light display that occurs in the upper atmosphere of a planet or moon. Auroras are caused by the interaction between the planet's magnetic field and charged particles from the solar wind. Earth's auroras are among the most well-known, but they also occur on other planets and moons with magnetic fields, such as Jupiter, Saturn, and Uranus. Dust storms. Dust storms are a common phenomenon on Mars, where they can cover the entire planet and last for months. These storms are caused by strong winds that pick up dust and sand from the surface and create massive dust clouds that can obscure the sun and reduce visibility. Dust storms on Mars can have a significant impact on the planet's climate and can affect the performance of solar-powered spacecraft and rovers. Geysers. Geysers are rare but fascinating phenomena that have been observed on several moons in the outer solar system, including Enceladus and Europa. These geysers are caused by the heating of subsurface oceans, which can create pressurized jets of water and other materials that erupt through the surface. Geysers on these moons are of great interest to astrobiologists, as they could potentially provide a habitat for microbial life. Cratering. Cratering is a common phenomenon on planets and moons in the solar system, caused by the impact of asteroids and comets. Craters can provide valuable information about the history of the solar system and the processes that have shaped the planets and moons over time. The Moon, in particular, is covered in craters, providing evidence of its violent past. Studying these phenomena can provide important insights into the geological, atmospheric, and environmental conditions of other planets and moons in the solar system, and help us better understand the processes that govern the formation and evolution of planetary bodies. Moreover, the study of these phenomena can also have practical applications for space exploration and colonization. For example, understanding the hazards posed by dust storms on Mars can help scientists design more robust and resilient spacecraft and habitats for future missions to the Red Planet. Similarly, studying the geysers on moons like Enceladus and Europa could provide valuable information about the potential habitability of these worlds, and guide the search for life beyond Earth. In recent years, advances in technology and space exploration have led to many exciting discoveries in the field of planetary science. For example, the recent landing of the Perseverance rover on Mars has opened up new avenues of research into the geological and environmental conditions of the Red Planet. Similarly, the upcoming Europa Clipper mission, scheduled to launch in the mid-2020s, will study the geysers and subsurface ocean of Jupiter's moon Europa in unprecedented detail. In addition to the astronomical phenomena mentioned above, there are several other interesting features and events that occur on planets and moons in the solar system. Here are some examples. Polar caps. Several planets and moons, including Mars and Earth's moon, have polar caps composed of frozen water and other volatile substances. Studying the composition and behavior of these polar caps can provide valuable insights into the history and evolution of these worlds. Dust devils. Dust devils are whirlwinds of dust and sand that occur on the surface of several planets and moons, including Mars and Earth's moon. These phenomena can be as small as a few meters across or as large as a kilometer or more, and they can have important implications for the transport of dust and other materials on these worlds. Transit events. Transit events occur when one planet or moon passes in front of another, as seen from Earth or from a spacecraft in orbit around a planet. These events can be used to study the atmospheres and physical properties of planets and moons in the solar system, as well as to search for exoplanets around other stars. Magnetic fields. Several planets and moons in the solar system have magnetic fields, which can have important implications for the behavior of charged particles and the formation of auroras. Studying the magnetic fields of these worlds can provide important insights into their internal structure and dynamics. Eclipses. Eclipses occur when one planet or moon passes in front of the Sun, as seen from another planet or moon. These events can provide valuable opportunities for studying the atmospheres and physical properties of these worlds, as well as for observing the Sun itself. Volcanism is a phenomenon that occurs on several planets and moons in the solar system. It is the process by which molten rock, ash, and gas are expelled from a planetary body's interior onto its surface. Volcanic activity can take many forms, ranging from gentle lava flows to explosive eruptions that can spew ash and debris thousands of kilometers into the air. On Earth, volcanoes are generally associated with tectonic activity, where the movement of the planet's plates can cause magma to rise to the surface. However, on other planets and moons, volcanic activity can occur for a variety of other reasons, such as internal heating caused by radioactive decay or tidal forces. Volcanoes on other planets and moons can be much larger and more active than those on Earth, due to the different geological and atmospheric conditions. For example, Olympus Mons on Mars is the largest volcano in the solar system, with a height of over 22 kilometers, and a base that covers an area roughly the size of Arizona. It is a shield volcano, which means that it has a broad, gently sloping shape that is formed by the accumulation of lava flows over time. In addition to Olympus Mons, Mars has several other large volcanoes, including Arsia Mons, Pavonis Mons, and Elysium Mons. These volcanoes are thought to have formed through a combination of tectonic activity and mantle plumes, where hot material rises from the planet's interior and melts through the crust to form volcanic vents. Volcanic activity has also been observed on several of Jupiter's moons, most notably Io. Io is the most volcanically active object in the Solar System, with over 400 active volcanoes that spew sulfur and other materials into space. The volcanic activity on Io is caused by the tidal forces of Jupiter and other nearby moons, which cause the moon's interior to flex and heat up, creating molten rock that rises to the surface. Studying volcanism on other planets and moons can provide valuable insights into the geological and environmental conditions of these worlds. For example, the composition of volcanic materials can reveal the chemical makeup of a planet's interior, while the shape and size of volcanic features can provide clues about the planet's past tectonic and volcanic activity. Moreover, studying volcanoes on other planets and moons can also help scientists better understand the behavior and evolution of volcanoes on Earth. Auroras, also known as the Northern and Southern Lights, are a spectacular natural light display that occurs in the upper atmosphere of a planet or moon. These phenomena are caused by the interaction between the planet's magnetic field and charged particles from the solar wind. The solar wind is a stream of charged particles, mainly protons and electrons, that flows outwards from the Sun at high speeds.
The Hertzsprung-Russell diagram, also known as the HR diagram, is a graphical representation of the characteristics and evolutionary processes of stars. The HR diagram plots the absolute magnitude of a star against its spectral type or surface temperature. The diagram is named after the Danish astronomer Ejnar Hertzsprung and the American astronomer Henry Norris Russell, who independently developed the diagram in the early 20th century. One of the most important features of the HR diagram is the main sequence, which is a diagonal band that runs from the upper left to the lower right of the diagram. The main sequence represents stars that are fusing hydrogen in their cores, which is the process that powers most stars, including the Sun. Stars on the main sequence range in mass from about 0.08 to 150 times the mass of the Sun, with hotter and more luminous stars located towards the upper left of the diagram. Another important feature of the HR diagram is the giant and supergiant branches, which are located above and to the right of the main sequence, respectively. These branches represent stars that have exhausted their core hydrogen and are expanding and cooling. Stars on these branches can have masses that range from about 0.3 to 100 times the mass of the Sun. The HR diagram also shows the evolutionary path of stars. As stars age, they move away from the main sequence and evolve along different branches of the diagram, depending on their mass. Low-mass stars, with masses less than about 0.4 times the mass of the Sun, evolve into white dwarfs, which are dense, compact objects that are supported by electron degeneracy pressure. Intermediate mass stars, with masses between about 0.4 and 8 times the mass of the Sun, evolve into red giants and then into planetary nebulae, which are expanding shells of gas and dust that are ejected from the star's outer layers. High-mass stars, with masses greater than about 8 times the mass of the Sun, evolve into supergiants and then into supernovae, which are explosive events that mark the end of the star's life. The HR diagram is a powerful tool for understanding the properties and behavior of stars. By studying the characteristics and evolutionary processes of stars on the diagram, astronomers can gain valuable insights into the formation and evolution of the universe. Moreover, the HR diagram has practical applications, such as in the determination of the distances and ages of stars, and in the search for planets and other objects around other stars. Another important aspect of the Hertzsprung-Russell diagram is the relationship between a star's luminosity, temperature, and radius. The relationship between these properties is known as the stellar mass-luminosity relation, which is a fundamental tool for studying the properties of stars. The mass-luminosity relation shows that more massive stars are more luminous than less massive stars of the same temperature. This is because more massive stars have higher core temperatures and pressures, which allow them to fuse hydrogen more rapidly and generate more energy. The mass-luminosity relation is important for understanding the distribution of stars in the galaxy, as well as for determining the ages and distances of stars. Another important feature of the Hertzsprung-Russell diagram is the instability strip, which is a region of the diagram that contains stars that exhibit variable brightness. Stars in the instability strip pulsate, or expand and contract, in a regular pattern, which causes their brightness to vary over time. This variability can be used to determine the intrinsic properties of the star, such as its mass, radius, and luminosity. The Hertzsprung-Russell diagram is also useful for studying the properties of binary stars, which are systems of two stars that orbit around a common center of mass. Binary stars can be used to determine the masses and radii of stars, as well as to study the effects of tidal interactions and mass transfer between the stars. In summary, the Hertzsprung-Russell diagram is an essential tool for understanding the characteristics and evolutionary processes of stars. The diagram shows the relationship between a star's luminosity, temperature, and radius, and provides important insights into the mass-luminosity relation and the instability strip. By studying the HR diagram, astronomers can deepen our understanding of the properties and behavior of stars, and unlock new insights into the formation and evolution of the universe. The Hertzsprung-Russell diagram is a two-dimensional plot that allows astronomers to classify stars based on their intrinsic properties. The diagram is divided into several regions, including the main sequence, giant branch, supergiant branch, white dwarf region, and instability strip. The main sequence is the region of the diagram that contains stars that are actively fusing hydrogen in their cores. These stars are categorized based on their spectral type, which is a measure of their surface temperature. The spectral types are indicated by the letters O, B, A, F, G, K, and M, with O being the hottest and most luminous and M being the coolest and least luminous. Above and to the right of the main sequence are the giant and supergiant branches, which represent stars that have evolved off the main sequence and are expanding and cooling. These stars have exhausted their core hydrogen and are now fusing heavier elements, such as helium and carbon, in their cores. As the stars evolve, their radii increase, and their surface temperatures decrease, causing them to move upwards and to the right on the diagram. The white dwarf region of the HR diagram contains stars that have exhausted all of their nuclear fuel and have collapsed to a very small size. White dwarfs are the remnants of low to intermediate mass stars, and are supported by electron degeneracy pressure. The instability strip is a region of the HR diagram that contains stars that exhibit variability in their brightness. These stars pulsate in a regular pattern, which allows astronomers to determine their intrinsic properties, such as their mass, radius, and luminosity. The instability strip contains several types of pulsating stars, including Cepheids, RR Lyrae stars, and Delta Scuti stars. The Hertzsprung-Russell diagram is an important tool for understanding the properties and behavior of stars. By studying the diagram, astronomers can determine the ages and distances of stars, as well as their masses, radii, and luminosities. The diagram also provides important insights into the formation and evolution of the universe, and is a fundamental tool for studying the properties of galaxies and other astrophysical objects. The Hertzsprung-Russell diagram is also useful for studying the properties of star clusters. Star clusters are groups of stars that form from the same cloud of gas and dust, and are therefore similar in age and chemical composition. By studying the distribution of stars in a cluster on the HR diagram, astronomers can determine the age and distance of the cluster, as well as the masses and luminosities of its stars. Another important application of the HR diagram is in the search for exoplanets, which are planets that orbit stars outside our solar system. By studying the properties of the host stars, such as their mass and luminosity, astronomers can determine the properties of the planets that orbit them, such as their size and distance from the star. The HR diagram is also useful for determining the habitable zone around a star, which is the region where a planet could have liquid water on its surface, and therefore the potential for life. The HR diagram has also played an important role in the development of our understanding of the structure and evolution of the Milky Way galaxy. By studying the distribution of stars in the galaxy on the HR diagram, astronomers can determine the ages and metallicities of stars in different regions of the galaxy, and use this information to develop models of the formation and evolution of the galaxy. Finally, the Hertzsprung-Russell diagram is a fundamental tool for testing and refining models of stellar evolution. By comparing the predictions of theoretical models with observations of stars on the HR diagram, astronomers can refine their understanding of the physical processes that govern the behavior of stars, such as nuclear fusion, convection, and radiation. In conclusion, the Hertzsprung-Russell diagram is an essential tool for understanding the characteristics and evolutionary processes of stars. Nebulae are among the most spectacular and enigmatic phenomena in the cosmos. These vast clouds of gas and dust are the birthplaces of stars, and they play a crucial role in the evolution of galaxies. In this article, we will explore the formation and distribution of nebulae throughout the universe. Formation of nebulae. Nebulae are formed when massive stars reach the end of their lives and explode in a violent supernova. This explosion releases huge amounts of energy and material into space, creating a shock wave that compresses nearby gas and dust into dense clouds. These clouds, which can be as large as hundreds of light years across, are the birthplaces of new stars. As the gas and dust in the nebulae begin to collapse under their own gravity, they heat up and start to glow. This glow is caused by the energy released as the gas particles collide and merge, a process known as fusion. Over time, the nebulae become denser and hotter, eventually reaching temperatures of millions of degrees Celsius. At these temperatures, the gas becomes ionized, creating the colorful nebulae that we see in photographs. Distribution of nebulae. Nebulae are found throughout the universe, from our own Milky Way galaxy to the most distant galaxies we can observe. They are particularly abundant in regions of active star formation, such as the Orion Nebula, which is located about 1,500 light-years from Earth. In addition to being found in galaxies, nebulae can also exist as isolated clouds of gas and dust in intergalactic space. These intergalactic nebulae are thought to be formed by the same processes as their galactic counterparts, but they are much rarer and harder to detect. One of the most famous nebulae is the Crab Nebula, which was created by a supernova explosion observed by Chinese astronomers in 1054 AD. The Crab Nebula is located in our own Milky Way galaxy, about 6,500 light-years from Earth. It is a source of intense radiation and is thought to contain a pulsar, a highly magnetized neutron star that emits beams of electromagnetic radiation. Conclusion: nebulae are among the most fascinating objects in the universe, and their formation and distribution provide important clues to the evolution of galaxies and the birth of stars. With advances in technology and observation, scientists are continually learning more about these spectacular clouds of gas and dust, and we can look forward to new discoveries in the years to come. In addition to their role in star formation and galactic evolution, nebulae also have cultural significance. For thousands of years, people have looked up at the stars and interpreted the shapes and patterns they see in the night sky. Nebulae, with their beautiful colors and intricate shapes, have inspired artists and writers throughout history. 1 example of this is the Orion Nebula, which has been observed and documented since ancient times. The ancient Greeks saw the Orion constellation as a hunter, and the nebula was seen as his sword or shield. In modern times, the Orion Nebula has been the subject of many scientific studies and has been photographed by numerous space telescopes. Nebulae also play a key role in the search for extraterrestrial life. Scientists believe that some nebulae may contain the building blocks of life, such as amino acids and organic molecules. By studying these nebulae, researchers hope to gain a better understanding of how life may have originated on Earth and whether similar processes could occur elsewhere in the universe. Nebulae are distributed throughout the universe in a variety of ways. They are most commonly found in regions of active star formation, such as spiral arms of galaxies and giant molecular clouds. These regions are characterized by high densities of gas and dust, which provide the raw material for new stars to form. Nebulae can be found in all types of galaxies, from small irregular galaxies to massive elliptical galaxies. In spiral galaxies like our Milky Way, they are often located in the arms of the galaxy, where the density of gas and dust is highest. In elliptical galaxies, nebulae are more widely distributed and tend to be less common. Nebulae can also exist as isolated clouds of gas and dust in intergalactic space. These intergalactic nebulae are thought to be formed by the same processes as their galactic counterparts, but they are much rarer and harder to detect. The distribution of nebulae also depends on their type. For example, emission nebulae, which are ionized clouds of gas that emit light, tend to be found in regions of active star formation. These regions are often characterized by bright, young stars that ionize the gas in the surrounding nebulae. Some well-known examples of emission nebulae include the Orion Nebula and the Carina Nebula. On the other hand, reflection nebulae, which are clouds of dust that reflect light from nearby stars, tend to be more widely distributed throughout galaxies. They are often found in the vicinity of star-forming regions but can also be found in more isolated regions of galaxies. One example of a reflection nebula is the Blue Snowball Nebula, which is located in the constellation Andromeda. Finally, dark nebulae, which are clouds of dust that obscure light from behind them, tend to be found in the same regions as reflection and emission nebulae. They are often located in the vicinity of bright, young stars, which illuminate the surrounding gas and dust. The Horsehead Nebula, which is located in the constellation Orion, is an example of a dark nebula. In summary, nebulae are distributed throughout the universe in a variety of ways, depending on their type and the regions in which they form. By studying the distribution of nebulae, scientists can gain insights into the processes that shape galaxies and the role that these enigmatic clouds of gas and dust play in the formation and evolution of the cosmos. Nebulae are formed when massive stars reach the end of their lives and explode in a violent supernova. This explosion releases huge amounts of energy and material into space, creating a shock wave that compresses nearby gas and dust into dense clouds. These clouds are often referred to as supernova remnants. The gas and dust in these supernova remnants are initially cold and diffuse, but the shock wave from the supernova heats them up and compresses them, causing them to collapse under their own gravity. This process of gravitational collapse causes the gas and dust to become denser and hotter, eventually leading to the formation of a protostar. As the protostar continues to accrete material, it heats up and eventually reaches a temperature at which nuclear fusion can occur. At this point, the protostar becomes a fully fledged star, and the surrounding cloud of gas and dust is known as a protoplanetary disk. This disk contains the building blocks of planets and other objects in the solar system, and it eventually gives rise to a planetary system. As the star continues to evolve, it emits high-energy radiation that ionizes the gas in the surrounding nebula. This ionization causes the gas to glow, creating the colorful emission nebulae that we observe in the night sky. The astronomy has come a long way since the invention of the telescope in the early 17th century. Today, astronomers use some of the most advanced technologies and techniques available to study the cosmos. In this article, we'll explore some of the most cutting-edge technologies and techniques used in modern astronomy. Adaptive optics. Adaptive optics is a technique used to correct the distortions caused by Earth's atmosphere on incoming light. This technique involves using a deformable mirror that can adjust its shape in real time to compensate for the atmospheric distortions. Adaptive optics is essential for ground-based telescopes, as it allows astronomers to achieve much higher resolution images than would otherwise be possible. Interferometry. Interferometry is a technique that combines the light from multiple telescopes to create a single, high-resolution image. This technique is used to study objects that are too small or too distant to be observed with a single telescope. Interferometry has revolutionized our understanding of the cosmos, allowing us to study everything from the structure of stars to the formation of galaxies. Gravitational wave astronomy. Gravitational wave astronomy is a relatively new field that involves detecting and analyzing the ripples in spacetime caused by the collision of massive objects, such as black holes and neutron stars. This technique involves using specialized detectors, such as LIGO and Virgo, to measure the tiny changes in distance caused by gravitational waves. Gravitational wave astronomy has opened up a new window into the universe, allowing us to study some of the most extreme and violent events in the cosmos. Spectroscopy. Spectroscopy is a technique used to study the chemical composition and physical properties of objects in the universe. This technique involves breaking down the light from an object into its component wavelengths and analyzing the resulting spectrum. Spectroscopy has allowed us to study everything from the composition of stars and planets to the history of the early universe. Space telescopes. Space telescopes, such as Hubble and Chandra, have revolutionized our understanding of the universe by providing high-resolution images and data without the distortion caused by Earth's atmosphere. Space telescopes have allowed us to study everything from the formation of galaxies to the search for exoplanets. Data science. Data science plays an increasingly important role in modern astronomy. With the explosion of data from telescopes and other instruments, astronomers must use advanced statistical and computational techniques to analyze and interpret the data. Data science allows astronomers to extract insights from large datasets and make new discoveries about the universe. Radio astronomy. Radio astronomy is a technique used to study the universe by detecting and analyzing radio waves emitted by celestial objects. This technique involves using specialized telescopes that are designed to detect radio waves, which can be used to study everything from the structure of galaxies to the search for extraterrestrial intelligence. Imaging and visualization. Imaging and visualization techniques are essential for studying the cosmos, as they allow astronomers to see and understand complex data and phenomena. Advanced imaging techniques, such as 3D modeling and virtual reality, allow astronomers to create realistic simulations of celestial objects and events, providing insights into the workings of the universe that would otherwise be impossible to see. Machine learning. Machine learning is an emerging field that is revolutionizing astronomy by allowing researchers to automatically analyze and interpret large datasets. Machine learning algorithms can be trained to recognize patterns and anomalies in data, allowing astronomers to make new discoveries and gain new insights into the cosmos. Data sharing and collaboration. Data sharing and collaboration are essential for modern astronomy, as they allow researchers to pool their resources and expertise to tackle some of the most complex and challenging questions about the universe. Advances in technology, such as cloud computing and big data analytics, are making it easier than ever for astronomers to collaborate and share their data with researchers around the world. Adaptive optics is a technique used to correct the distortions caused by Earth's atmosphere on incoming light. The Earth's atmosphere contains pockets of air that have varying temperatures, densities, and pressures. As light from celestial objects passes through these pockets of air, it is bent and distorted, causing images of stars and other objects to appear blurry. Adaptive optics corrects these distortions in real time by using a deformable mirror that can adjust its shape up to thousands of times per second. The deformable mirror is controlled by a computer that analyzes the distortions in the incoming light and calculates the corrections needed to create a clear image. The mirror then adjusts its shape to compensate for the atmospheric distortions, creating a sharp, high-resolution image. Adaptive optics is essential for ground-based telescopes, as it allows astronomers to achieve much higher resolution images than would otherwise be possible. Without adaptive optics, ground-based telescopes would be limited by the distortions caused by the Earth's atmosphere, making it difficult to study fine details in celestial objects. Adaptive optics is also used in other applications, such as laser eye surgery and microscopy. In both cases, the technique is used to correct for distortions caused by the medium through which light is passing, allowing for clearer images and better results. In summary, Adaptive optics is a critical technology for modern astronomy, allowing ground-based telescopes to achieve much higher resolution images than would otherwise be possible. The technique is also used in other applications, such as laser eye surgery and microscopy, where it is used to correct for distortions caused by the medium through which light is passing. Interferometry is a technique used in astronomy to combine the light from multiple telescopes to create a single, high-resolution image. This technique is used to study objects that are too small or too distant to be observed with a single telescope. Interferometry has revolutionized our understanding of the cosmos, allowing us to study everything from the structure of stars to the formation of galaxies. Interferometry works by combining the light from multiple telescopes and analyzing the resulting interference pattern. The telescopes are precisely aligned and positioned so that the incoming light waves interfere constructively, creating a pattern of bright and dark fringes. The pattern is analyzed using sophisticated algorithms, which can reconstruct the image of the object being observed with much higher resolution than would be possible with a single telescope. One of the key advantages of interferometry is that it allows astronomers to achieve much higher resolution images than would be possible with a single telescope. This is because the resolution of a telescope is limited by its diameter, with larger telescopes capable of resolving finer details. However, building a single telescope with a very large diameter is difficult and expensive. Interferometry allows astronomers to achieve the same level of resolution by combining the light from multiple smaller telescopes. Interferometry is used in a wide range of applications in astronomy, from studying the atmospheres of exoplanets to imaging the black holes at the centers of galaxies. One of the most exciting recent applications of interferometry is in the study of gravitational waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo Interferometer use interferometry to detect the tiny changes in distance caused by gravitational waves, allowing astronomers to study some of the most extreme and violent events in the cosmos. Data sharing and collaboration are critical to modern astronomy.
Light is an important aspect of the universe, and it provides valuable insights into the nature and behavior of celestial objects. There are several interesting light phenomena in the universe, including rainbows, light rays, and lightning. Rainbows are a beautiful and fascinating light phenomenon that occurs when sunlight is refracted and reflected by water droplets in the air. Rainbows typically appear when there is rain or mist in the air, and they are formed when the sun's rays pass through the water droplets, causing them to bend and reflect the light in a spectrum of colors. Light rays are another interesting light phenomenon that occurs in the universe. Light rays are beams of light that are visible when the light passes through a medium with different optical properties than the surrounding environment. This can occur, for example, when sunlight passes through a window or when light passes through a crystal or prism. Lightning is another fascinating light phenomenon that occurs in the universe. Lightning is a powerful electrical discharge that occurs during thunderstorms, and it is caused by the buildup of static electricity in the atmosphere. When the electrical charge becomes too great, it is discharged as a bolt of lightning, creating a bright flash of light and a loud clap of thunder. In addition to these phenomena, there are many other interesting light phenomena in the universe, including auroras, mirages, and halos. Auroras are colorful displays of light that occur in the polar regions when charged particles from the Sun interact with the Earth's magnetic field. Mirages are optical illusions that occur when light is refracted by the Earth's atmosphere, creating distorted images of distant objects. Halos are circles of light that appear around the Sun or Moon, and they are caused by the refraction of light by ice crystals in the atmosphere. The study of light phenomena in the universe is important for understanding the nature and behavior of celestial objects. By studying the properties and behavior of light, scientists can gain insights into the composition, structure, and dynamics of the universe. Light phenomena also provide valuable information about the atmosphere and other environmental conditions of celestial objects. Another interesting light phenomenon in the universe is known as gravitational lensing. Gravitational lensing occurs when the gravitational field of a massive object, such as a galaxy or a cluster of galaxies, bends and magnifies the light of more distant objects behind it. This phenomenon was predicted by Einstein's theory of general relativity and has been observed and studied by astronomers. Gravitational lensing can provide valuable insights into the distribution and properties of dark matter in the universe, as well as the structure and evolution of galaxies and galaxy clusters. Another fascinating light phenomenon in the universe is known as the cosmic microwave background radiation. This is the afterglow of the Big Bang, which occurred about 13.8 billion years ago. The cosmic microwave background radiation is a faint glow of electromagnetic radiation that permeates the entire universe, and it is thought to be the oldest light in the universe. The cosmic microwave background radiation can provide valuable information about the early universe, including the conditions that existed shortly after the Big Bang. By studying the properties and behavior of this radiation, astronomers can gain insights into the structure and evolution of the universe, as well as the properties and behavior of dark matter and dark energy. Finally, another interesting light phenomenon in the universe is the phenomenon of black holes. Black holes are objects with such strong gravitational fields that nothing, not even light, can escape them. However, black holes can emit light in the form of intense radiation from the matter that is being pulled into them, known as accretion disks. The study of black holes and their radiation can provide valuable insights into the properties and behavior of these enigmatic objects. By studying the radiation emitted by black holes, astronomers can gain insights into their mass, spin, and other properties, as well as the behavior of matter in extreme gravitational environments. Gravitational lensing occurs when a massive object, such as a galaxy or a cluster of galaxies, bends and magnifies the light of more distant objects behind it. The light passing close to the massive object is deflected by the gravitational field of the object, causing the light to bend and magnify. This effect is similar to the way a lens magnifies and focuses light in a telescope or camera. Gravitational lensing is an important tool for astronomers to study distant objects in the universe, such as galaxies and quasars, that would otherwise be too faint to observe directly. By observing the magnified and distorted images of these objects, astronomers can gain insights into their properties, such as their mass, structure, and distribution of dark matter. Gravitational lensing can also provide information about the properties of the lensing object, such as its mass and distribution of dark matter. The cosmic microwave background radiation is a faint glow of electromagnetic radiation that permeates the entire universe. This radiation was emitted about 380,000 years after the Big Bang, when the universe became transparent to light. The cosmic microwave background radiation is thought to be the oldest light in the universe and provides valuable information about the conditions that existed shortly after the Big Bang. By studying the cosmic microwave background radiation, astronomers can gain insights into the composition and structure of the universe, as well as the properties of dark matter and dark energy. The cosmic microwave background radiation provides a snapshot of the early universe and can help astronomers understand the processes that led to the formation of galaxies and other large-scale structures in the universe. Black holes are objects with such strong gravitational fields that nothing, not even light, can escape them. However, black holes can emit light in the form of intense radiation from the matter that is being pulled into them, known as accretion disks. This radiation can include X-rays and gamma rays, and can be detected by telescopes and other instruments. The study of black holes and their radiation can provide valuable insights into the properties and behavior of these enigmatic objects. By studying the radiation emitted by black holes, astronomers can gain insights into their mass, spin, and other properties, as well as the behavior of matter in extreme gravitational environments. Black holes are also thought to play a significant role in the formation and evolution of galaxies and other large-scale structures in the universe. Another interesting light phenomenon in the universe is known as the redshift of light. This phenomenon occurs when light from a distant object is shifted towards longer wavelengths, such as towards the red end of the spectrum, as it travels through space towards an observer. The redshift of light is caused by the expansion of the universe, as the light is stretched out by the increasing distance between the object and the observer. The redshift of light is an important tool for astronomers to study the properties and behavior of objects in the universe, such as galaxies and quasars. By measuring the redshift of light emitted by these objects, astronomers can determine their distance from Earth, as well as their velocity and direction of motion. This information can provide insights into the structure and evolution of the universe, as well as the properties and behavior of dark matter and dark energy. Another fascinating light phenomenon in the universe is known as polarized light. Polarized light is light that vibrates in a specific direction, rather than in all directions, and can occur when light passes through certain materials, such as crystals or polarizers. In the universe, polarized light can occur in a variety of situations, such as when light passes through dust or gas in space or when it is emitted by certain celestial objects, such as pulsars.